All right, does it work now?
Yeah. Yeah.
Okay, so here's the easiest problem, J, frosting on the cake. Basically, you have a square, or not necessarily a square, but like a rectangle, and it's split into n columns and n rows, and so each row or each like square produced by the intersection of a column and a row is colored in a pattern like if like the first row is index is 1 and then the first column index is 1, then you put color 2 in here because 1 plus 1 mod 3 is 2. And then so you basically follow this pattern throughout the entire one, and through the entire rectangle, and then you're asked to find the like the total area covered by each color. And so the key thing to note here is that for each row, it's like it's basically the colors are rotating based. So if you just say you fix the columns and then you check like every sum up every third column, you get all the colors for a single or you get all the area for a single color. And if you go down a row, you notice that, like for example, here I sum up A1, A4, and AN for the white squares. If you go down a row, you see that it's the sum of A1, A4, AN for orange now. And so it's the colors are just rotating. So you can just multiply like each of like the summed columns for each of the row depending on what the index of the row is, and then you just sum it all up. So this was like a pretty simple one. The next easiest one I believe was A at the top. Here. Okay. So here it says Cakey McCakeFace's signature pastry, the unknowable cake, da da da. And basically we have like sort of like a conveyor belt going through an oven. And every single time we put a cake on the conveyor belt and it enters the oven, there's like a record that keeps track of when a cake enters the oven. And then exactly let's just say K seconds later, it says cooking time. I'm just going to give it K, exactly say K seconds later, it will leave the oven. And there's also a counter that tracks exactly when it leaves the oven. Um, Unfortunately, we're given a bunch of numbers that aren't necessarily exactly the times. Like all the times that a cake enters and leaves the oven are included in these numbers, but aren't necessarily the only numbers. So like there could be false numbers in this output. So for example, here the output is 5K. We find K equal to 5, but obviously 1 can't be like a time where the cake leaves the oven, and 10 can't be a time where the cake enters the oven because there's no 15 on this row. So we're asked to find like the K such that the maximum number of pairs of cakes that enter the oven and maximum pairs of cakes that exit the oven have this K. And so essentially this is like a brute force because for every single so we see that N and M are exactly 2000 here. So we can just brute force and compute every single pair of exit times and enter times, and then simply take the max, like the number, find the difference between the exit time and the entry time, and then group them all together, and then find the maximum such number, such that like the pairs of exit and entry are.
Yeah, so I'm curious whether this question had a lower than quadratic solution. So just out of curiosity, I don't know.
It probably does because we're given these in like sorted order, so you could probably do some like 2-pointers thing, but the brute force works.
It's not clear how. So I was.
Oh, that's true.
Yeah. So
I don't know, but
okay.
it's low. The limits are low
Right.
enough.
Yeah,
So
I know that. Yeah.
yeah. Okay, and then the third easiest problem was C, macarons. So essentially, this is like a twist on like the normal bit mask DP type problem, where you have to tile an n by m table with squares of size 1 by 1 and rectangles of size 2 by 1 or 1 by 2. And I should, for the two that are in here that may not be familiar with bitmask DP, I'm just going to go over it real quick. So first thing to note is that n is small and m is large. And because n is small, we can do DP on like do like a kind of like a state analysis on this problem. So essentially, imagine like maybe we have, let's just say we have like 3 here because 3 is a small easy number. So we can consider the states here as like the states for the DP as how many boxes are filled up from the previous row. So like, for example, let's just say in this first row here, we fill in this box like this, and then we fill in the 2 little boxes like this. Okay, so in here, we'll see that this, like doing this gives us a state of like that this box is filled while these 2 boxes are not filled. And then we want to see how many ways are there to move from this state into a filled like second row that might spill over into the third row. So let's just say we might fill in boxes like this. And this is a valid solution of like filling boxes that fill up the second row, and a little bit spills over into the third row. And then so we get this state for the third row, and we kind of just like find a relationship between each row, like based on a state. So that's like this state might start off 0, 0, 0, and there are like 2 ways of turning this into 1, 0, 0 on the next row while filling up this first row. So like we could have done this here, and then the 2 small boxes before, or we could have put like a 2 by 1 box like this. So there's 2 ways. And then similarly, we can check how many ways there are of making this into 0, 1, 0, and basically do this across all states. It's like, this is kind of like a quick explanation of bitmask DP, and you should probably look into more if you still don't understand, but yeah, that like the quick example is really what.
So how exactly did you compute this correspondence? Did you do it for every starting state and every ending state? So
yes, I computed it for every starting state, every ending state, and there's a interesting thing you could do with Fibonacci numbers here, because you can note that if you want, if we do like this in the 1D case, let's just say we have a 1D case here with a bunch of like squares like this. And you want to fill this up with either only size 1 boxes or size 2 boxes. So this relationship corresponds exactly to the number of the Fibonacci number sequence, right? Because if you wanted to fill up 0 boxes, there's exactly 0 ways of doing it. If you wanted to fill up 1 box, there's exactly 1 way, putting putting a single box like this. If you wanted to fill up like 2, then you can either do that or this. If you fill up here, then note that you can either place a box like this or a single box like this. And then so you just sum up these 2, and then so this turns into the Fibonacci sequence, right? And so what you can do is in this 2D case, we note that every single time that we need to fill up like a row, we need to fill in all the zeros in that row. And in order to transition to a new state, let's just say this 0, 1, 0 state wants to transition into like 1, 0, 0 state, then any next state with a 1 in it has to be filled in by a 1 by 2 box placed horizontally. So
we cannot we do 2 1 by 1 box?
We can't do 2 1 by 1 boxes because we want to make sure that this is filled in, like the next row's one is filled in. So if we drew this out,
If you are using a 1x2, you can replace that 1x2 with a 2 1x1, right? So because
Right,
this is
but
slightly different from the filling only with 1x2. This is you can also use 1x1.
right, but I'm considering only the case where I only place boxes that have at least one square inside this row. So if this box is already filled
Okay.
in, and I want to fill in these two boxes right here, then the only way I can do that is either with two 1x1 boxes, one here,
Mhm.
and then or I can fill in like a 1x2 box here or 1x2 box here, and then fill in the next one here. And those all give different transitions to the next state. So for example, 0, 1, 0 would have a transition to 0, 0, 0 would have to 1, 0, 0, 0, 0, 1, and 1, 0, 1.
So then from this transition, so you are going to compute in the end, you're going to compute the matrix, right?
Yes, I'm going to compute a matrix for every 2 to the n
State
to the n states.
right. So
And,
for each
yeah.
cell, you compute the transition, and then how do you get to the
Right. So let's just see. I'm gonna move this down a little bit. So we can compute the transition. The details I guess I'm just not gonna go over anymore. But now we have like a big matrix, right? And the problem is if we look back at the problem, we have m is less than 10 to the 18th, which is too big if we wanted to compute it like iteratively. But one thing we could do is notice that because this transition matrix is going to stay the same, we can just use exponentiation by squaring, because every single transition from one row to the next is basically a multiplication by this matrix. So if we have m, we can just multiply this matrix, basically if we need to go up to m, we need to take this matrix to the mth power and then multiply it by initial state, initial state, which corresponds to 0, 0, 0, 0, 0.
Yeah, so I know, yeah, you need to do this square and multiply algorithm for computing.
Right. So we can just do that. And the time complexity ends up being 60 times 256 to the third, because matrix multiplication is n cubed. And this is approximately 10 to the 9th. And I originally thought that this would be too slow, but Trung explained that because matrix multiplication is usually only like with a bunch of additions, and addition is a really fast operation. So this actually passed in actually under 1 second.
Okay. Okay, yeah, I guess so. I still not totally sure how to compute the one value in the matrix because of this. I find this having a 1x1 mess things up a little bit, but yeah, I think we can. Maybe I'll just okay, yeah. Could you send me your code? I'll take a look.
I should be able to explain it actually. It's like
Okay.
not that bad.
Okay.
So let's just say we have a like here, and we have already some cells filled in. Let's just say like this cell is filled in. This cell's filled in already from like the previous row.
Right.
Okay, and then we want to make sure that this next row, let's just say, has this cell filled in. Okay. For example, first thing you have to notice is that if these two have like the same cell filled in, so for example, if this is filled in, then we can't do this because we can't place any block that is contained in this square that also fills in this, because this is already filled up.
So this is so why you can why you cannot do why you cannot put a 1x1 in the new cell?
So because we're only filling in this row. We're only filling in the first row. We're not putting anything that's contained only in the second row.
Why?
can
But isn't it what we want is to figure out the number of ways to go from the previous state to this row using either 1 by 1 or 1 by 2.
Right, but the way I construct my DP is that you can only place either these types of blocks, you can only place these blocks,
And
or
then
you can
because
play
the
these.
rest of them,
Because if we wanted to place one in this row like this, we could just like do it in this state.
I see. I see. That's how you. Yeah, I guess I would. Okay, so that's how you deal with it, because I find this is the part that make the thing complicated, because the 1 by 1s you can, once you decided, you can put them. I see. So your state only consider the ones that are filled by 1 by 2s.
Yes.
I see. I see.
So
I see.
so given that like we have so basically if any two of them have like are filled in like the same row, then it's impossible because we can't fill it in the other way. We can't fill in like a single one on this one, for example. So also note that if this row, if the first row is not filled, if the first column is not filled and the second column is filled, like here, then we have to place this block, no matter what. So that's like fixed. Because we can't place any other block that fills in the second column, like this cell, without like messing it up.
But but you can use a 1 by 2 vertically in the second column, right? So that is considered allowed. That's counted in your state.
Yes, I can do this, right? Or I can do this.
No, I mean, if you have 2 consecutive in the second one, so if you have another filled block in the second row on top of the one you have, then filling those 2 with the 1 by 2, that's considered, so that is allowed, right?
Filling those.
You're just
so
adding
like,
another. So in your
here?
no, yeah, change your ending state so that the on top of the one field you have another one that's filled. So you have 2 consecutive filled.
Oh, so like this?
Yeah. So
Yeah.
in this case, you can fill 2 vertical. You can use 2 vertical 1 by 2, right?
Right, but if the thing is, we're also not considering this block at all, because that block doesn't have any. This doesn't fill any blocks in here.
Oh, so you only consider your state only consider. I see. I guess so long as you're consistent, that's that'll be
Right.
okay.
So
you're just defining one to be.
Oh my god.
Right, yeah, somehow the voice is a little bit strange. It's still maybe Chuang, can you mute to see whether that's the.
Okay, what about you? Is it better? No.
Oh my god.
That's still the audio. All right, so then yeah, let's I guess wrap this up.
Do you want me to explain mine?
Wait, I can
you have a
explaining
solution
this.
for this, or do you want to explain the next problem?
Yeah, no, the next problem.
Sure. Yeah.
I
So
can
Richard,
finish
are you down
Yeah.
with it? Yeah.
Wait, I can. It's really close to finish.
Okay.
All
Yeah.
right. Yeah, let's go on.
Okay. Yeah. Anyways, so basically, whenever we see that the second row is filled, we have to place like a 1 by 2, and so that's like fixed. We have to do this, right? So if we OR the 2 columns together, we see that we get a new column here that have like fixed, that have a bunch of fixed cells, and that we know that they have to be a specific one. And then now we're just left with a bunch, we're left with back with the 1D case. We have to fill this in with either 1 by 1s or 1 by 2s, like this.
Let me see.
And then so for each grouping of zeros, or I guess each grouping of empty cells, we compute it and then multiply each of them together. And then that's where the Fibonacci numbers come in.
Okay.
And then you can just like see how many there are and then compute it. Yeah.
Okay. Cool.
So that's how you compute the matrix, and then you have like the whole matrix multiplication thing, and then yep, it passes.
Okay. So
All All right, cool.
Yeah, so I guess then maybe you can stop sharing and
Yep.
Sean can.
I can still send my code in the chat real quick if you want to
Sure.
see it, but
Sure, yeah, please do that. Yeah.
but yeah.
Can I just check my link's working fine now?
It's similar. Yeah.
Yeah, it's still ruined.
Still.
All right. I'll do mine first really quick. All right. So I did, well, not like I did, but I coded B. Oh, sorry, I'm not the host. Can you share with the host with me?
Did you? I saw that.
All right, cool. Share screen. Wow. All right, can you see this?
Yes.
All right. So the problems that I did were B, but I thought about E, D, and G. But yeah, let's talk about B first. So basically, they give you like a rectangular grid with some cells that are filled with black, basically, and some other cells are filled with white. Let's think for this problem. Let's think as of black cells as like obstacles, and white cells are like open fields. So they basically ask like some queries where each query they'll give you 2 dimensions, the height and the width, and they ask you how many ways to fit a rectangle with these dimensions that onto this rectangle that is completely on the white squares, basically. So like the rectangle being put in must not overlap with any obstacles.
Sean, did you maximize your window or
Huh? Did I what?
Maximize your window or
I did maximize my window.
Okay.
Is it weird?
Maybe it's okay. I guess that's my view thing. Yeah.
Okay, can you see it?
Okay. Yeah, I can see it. Yeah. It's
All right.
just yeah.
Okay, cool. So yeah, they ask, like they give the 2 dimensions and they ask how many ways you can fill, like you can put the rectangles in that only overlaps over the white squares. Constraints are like 2,000 for the grid, both dimensions, and 100,000 queries. So cool. Let's start. Okay, so wait, hello. Oh,
Yeah.
there it is. No, here it is. So I will draw the grid first. So let's say like these rectangles are black. So suppose you want to fill in like a 2x3 rectangles into the white squares. So we know that like if we want to put it like right here, then this top cell must has at least three cells to the right of it, including that cell. And the cell below it must also have 3 white cells to the right of it, including that cell. Okay, so if you like, so what I did was basically I find the range of white cells, the range of columns that such that each cell in this column has at least 3 right cells to the right of it. Three white cells to the right of it. So basically like these 3 cells that are in the same column, they all have 3 white cells to the right of it. This cell has 3 white cells to the right. Also, this cell has 3 to the right. This has 3 to the right. This has 3 to the right. And also this has 3 to the right. So basically I transform like these cells into a bunch of ranges. Each range lies within like exactly 1 column. Can you see this?
I can see it. So do you pre-compute for each cell like how?
Yeah, I pre-compute for For
Mhm.
each cell, I pre-compute how many cells that are free to the right of it, like that are
Okay.
white to the right of it, including that.
So
And then-
basically, each cell is a number. So at this
Yes.
point, and then what are you looking for? Yeah, given
And
the
then,
number.
and then like for each cell, I compute to the right. And then for each column, I compress down like the cells that have at least 3 columns to the right, 3 white cells to the right of it. Like for every cells that can be like the first can have 3 white cells to the right, I compress them into one range. So like this is one range because all of them have 3 to the right. This forms a range, this forms a range, this forms a range, and these two forms a range.
So are you answering? Are you doing this for each query particularly, or this is a pre?
No, this is just like my thought process. I will
Okay.
tell
Okay,
about
okay.
like how to maintain, like how to do it for every query. So like we have these ranges, right? So we know that all of these cells have 3 to the right. So this is already done. We know that we must choose one of the top, like one of the cells within these ranges to be the top cell, top left cell. So the other question is that how can we satisfy this constraint? So to satisfy the constraint, we know that like if we have a range and we want to choose a top cell in this range, we know that the top cell must has at least 2 white cells below it in that range, including that cell. So for example, for this range right here, it corresponds to this. That means that this cell and this cell can be the top left cell of like a rectangle, but not this cell, because if we use this as the top left cell, then the rectangle will span under this. So that means that this, sorry, let's use another color. So if we choose this as a top left cell, then the rectangle will span under, and then it will hit like an obstacle. So like for each range, we know that some prefixes of it can be the top cell and others are not. Right? Is this clear to you?
Yeah.
Okay, cool. So we can actually compute the number of cells that can be the top left. So let's say that the length of this range is S, and this value is M. Then the number of cells that can be the top left will be S minus M plus 1. But this is taken max with 0 because like there are cases where the range is just too small, it cannot have any top cell. All right, cool. So yeah, so we basically have a bunch of these cells, and we can calculate the answer using this and sum it over every range. So how do I apply this to the whole problem? So to apply this to the whole problem, I will first split this condition into this. If S is larger or equal than M, then the answer is S minus M plus 1. Else, if S is less than M, then the answer is 0. So
What are S and M again?
S is like the size of the range, the length of the range, while M is the other dimension of the rectangle that we need to satisfy.
So S is the range of the number of this vertical number, so that they are all greater than equal to the
this dimension to M.
Yeah. Okay.
Yeah. So S is like the number of consecutive cells that they have at least n white cells to the right. And M is like the height dimension of the rectangle that we need to satisfy.
Right.
So for a range of height S, for a range of size S, if S is larger or equals than M, then we know that it will contribute S minus M plus 1 to the answer. But if S is less than M, then it will contribute 0 to the answer. So what is really important here is S. And also what's important in this in this is also S and minus M. So what I do is I basically store a data structure that can that can query two things. The first thing is how many elements is larger or equals than m, and the number of elements that is larger or equals than m will be contributed by multiplying with m and then minus to the answer, because sorry, like if we take the sum of s minus m plus 1 such that s is larger than m, that is equals to the number of elements that is larger or equals than m times m minus 1, and this is minus the sum of all elements s that is larger or equals than m. So these two expressions are the same, right? Did you get this?
You need some
Yeah.
time to power. Yeah. So this
So
is
like this expression is equals to this, where this is like sum of all elements that is larger or equals than m, and this is like count of all the number of elements that is larger or equals than m. So yeah. Like my thought process is that I take all of the ranges, I take their sizes, and then I put them into this data structure. And then when I need, I just like when I need to query, I just take the m from the query, and then I calculate sum of s such that they are larger or equals than m, and count of s such that they are larger or equal than m.
so yeah. What so yeah, maybe you just describe your algorithm. So starting from your first compute to the
Yes. So,
yeah.
so this is not my whole algorithm. Like
Okay,
this is
okay.
just my thought process. I will like describe the whole algorithm
Okay,
later.
okay.
So like currently I'm fixing n. So like if I fix n, this is my thought process. If I fix
Okay.
n, then I can compute these ranges. So after I compute these ranges, I can then take their sizes. And then because for any m that you give me, I can compute the answer such like this. I can basically put all of the sizes of the ranges into a data structure that can support finding sum of s such that they are larger or equals than m, and they can support finding count of s such that they are larger or equals than m.
Okay, I think just go on. Yeah, I'm not getting
All right,
on,
all right.
but yeah, so
All right,
yeah,
okay,
which is
cool.
fine. Yeah.
So anyway, so what I just described is an algorithm that solves for fixed n. So how can I solve for unfixed n? So I imagine okay, so I imagine like the operation as like iterating n from 1 to the maximal value that n can be. Then like for each cell, we know that at some point it will become like it will not be usable. Like for example, at n equals 2, as an example. So for example, at n equals 2, this range is actually usable because it has like two cells to the right of it. So at n equals 2, it like forms a whole range with this with these two cells. But at n equals 3, this cell does not like becomes unusable because it does not have like three free cells to the right of it. So I cut it from here, and then I split the range into the upper half and the lower half. So then like my whole solution is to first have like all of the ranges ready, and then I iterate n from the 1 to the max value it can have. At each value, I then like basically find all of the cells that becomes unusable, and then I cut it from its respective, like I cut it from the range that is currently containing it. While cutting it, I will also maintain this data structure that holds the sum and the counts. And then after like I have cut all of the cells that are unusable, I will use the data structure to answer the query for all of the rectangles such that its n is equals to the n that we are iterating over. And then I just query with this m. So yeah.
I see.
That's the whole algorithm.
I see.
Yes. So it is a bit complicated, but
Yeah, but yeah, I think I get I get the high level idea, and I felt that I learned something. So I guess the so this offline processing and processing the order based on n, this will be based on n gradually increasing, because initially all of you have more of this, and then
Yes.
while n increase, then
then some will disappear, and then
yeah,
you
some will
will split the
disappear.
ranges.
Yeah, and then you, so this is the what you are describing here is just to make the computation for all the query for same n to be efficient enough.
Yes.
Yeah.
So you can think of this like a problem that has sweep line, where the sweep lining here is for n,
Yeah.
and then
yeah.
you maintain a data structure over n. This is very popular. It is very like popular among like data structure problems.
Yeah.
Very cool. Okay, cool. Let's that's C. Let's look onto D. So for D, so basically you have like a string of candies, I think. Let's just say it's a string. So you can process this string as follows. So you have like a bunch of other strings that they give you, and each of the string has like a score. So here ICPC has a score of 5, ICPC has CPCI has a score of 1, and so on. Each query, like you can do this operation many times. Each time you will like take a substring of the original string, such that this substring is equals to one of the strings under here. You cut it from this big string, and then you add like this value to the score that you have. So for example, nope, not get it. Nope. Okay, right, there we go. Nope, not this. Sorry, my computer is a bit slow. So just as an example, there you go. So your score initially is 0. So you can repeatedly do something like this. So you choose the string ICPC here, you remove it from the big string, and then you add 5 to the score you have. And then repeatedly you remove like XXX here, which has score of 0, and then you add 0 to the score you have, which is also 5. And then you remove ACM, which has score of 10. So you have 10 added to your score. And then you also remove like ACM here, which has 2, 17, ACM here, which has 2, goes to 19, and ACM here. Okay, so the thing with this problem is that like a string can be like same as the string below or same as the reverse of the string below. You can just remove either way. So you can remove this because it's the reverse of ACM. So you add also 2 to like the score. So they want to ask you like, what's the maximal score that you can have just repeatedly do the operations. You don't have to like fully destroy the original string, but you need to maximize the score. So yeah, that's the process of this problem. There are like 50, the strings originally has 50 characters, as well as all of the strings below here. There are 200 strings given with the scores. Score is like 100, a million, and yeah, lowercase. That's just for sanity check. Cool. All right, so this problem is actually pretty hard. I'm not gonna lie. So the solution is to use a very kind of unintuitive DP. It's very difficult. So the DP.
I was when I read the problem, I was wondering whether kind of doing exhaustive search and storing the substate would be sufficient, but I saw so few people actually solve it. So
Yep. So that's my submission as well. So later on, like I read the slides, I gathered like all my others thoughts, and yeah, I can see that like the solution that the types gave, it's pretty intuitive, but it's also like the most efficient you can do. I think there are many things that are similar to this, but anyway, so the DP here consists of left, right, string, like substring, prefix, and consumption. Okay, I will explain all of this. So the DP here is like left, right, substring, prefix, consumption, which is like what is the maximal score that you can gain from left to from the substring left to right on the original string, such that like for a substring of size, like for a substring, which is denoted by the index here, for a substring here, we have like a prefix of that substring is like created by, oh, let me just write this.
First, what are the
maximal-
type? What are
Huh?
the type of left, right? So are they all
Oh, left is-
indexed into something, or
Left is like integer, like
it's is indexed into the string,
left,
or just
right is like the range of the original string.
okay.
So they are integers such that 1 less than equals to left, less than or equals to right,
Okay.
and less than or equals to s, where s is the string.
String length. Or,
No,
okay,
s is the
okay,
string.
good.
Yeah, cool. The substring here refers to like the index of the string here.
So okay,
Yeah, so like
one of
which,
this. Okay.
yeah, one of those.
And prefix.
And okay, prefix is a bit difficult. So consumption here is referring to like, do we need to like completely like consume every characters from left to right?
Okay, so I guess you're going to write the definition of
Yes,
this.
yeah, I'm
DB,
going
yeah,
to write the
yeah,
definition.
yeah, and then
Maximal
let's see.
score to solve S from left to right. If we need to, and whether we need to delete every characters from left to right. This is denoted by consumption, like whether this is denoted by consumption, such that the prefix of the substrings strings is created. Yeah, I'll just read the slide again because it's very intuitive. Where it is, where is it? There we go. So like the prefix from 0 to k, let's just denote this as k. Yeah, prefix size. So the prefix of 0 to prefix size of the substrings of the J substring is created from S from 0 to left -1. So intuitively, you would think of this as like we know like the some prefix of this of this J substring is already created to the left of this DP. So you just need to create some more to the right, like from left to right. Yeah, it's kind of weird.
Okay. So consumption is Boolean, right? So
yes. So
okay.
Yeah, consumption is like if we need to clear all of the
Right.
characters from left to right.
I see. So that's
All right. If you have like more questions, I will just link the slides of the solution, or you can.
we
just
don't. We don't have to cover every problem. If it's too hard, there's no need.
Okay, cool. Sure. So
but I guess at this level, I think it kind of makes sense. It's kind of given a sub problem, there's really many things you want to know. So that this will impact how this this will impact how you use the solution to the sub problem to solve the bigger one. So I guess obviously whether you've in the end get rid of all of them will matters. And I guess this prefix and J is kind of your, this is kind of you are determined to apply the J's thing, and because you already have some prefix, so then within this range you only need the later part.
Yes, that's correct.
Yeah.
So yeah, so from that like definition, we can clearly see that if like the left's character of S can extend this prefix right here, can extend the prefix of the J string, then we will need to like include it into the answer. So that will make like the one substate will be dp left plus 1 right J prefix size plus 1 because we have extended like the prefix, and then also consumption. However, if we are not able to do that, doesn't matter if we are able to do that or not. So suppose that we are not able to do that, then we need like this prefix size plus 1 character of the J substring of the J string must lie somewhere between left and right, right? So like, for example, if we need to extend the prefix of the J string at position K, then where at position K, where left less than or equals to right, less than equals to K, less than or equals to right, then we will need like the substring from left to K minus 1 to be completely cleared. Like it needs to be completely deleted, so that like if this is the case, then we need the substring S from left to K minus 1 to be completely deleted, so that the K character here of S can like go forward and then join with like the prefix before that, so that it can extend this prefix.
Yeah. I think it's okay. I guess the message is you maybe some of the state you can discover while you try to solve this in DP. You consider a substring, and then you want to use that, and then you see you need add some extra state, and you need then some additional extra state. So yeah, at this point, at least for me personally, this is kind of beyond my expertise. So
yeah,
getting some high level idea for me, I'll be, yeah.
I think it's very hard for me to understand it at first too. Yeah, so I'll probably skip this, but I'll link to the slides. Okay, so the other problem that I talked about, like that I solved, was H, but I think H is even like a big more difficult DP than D. It's just like more standard in my opinion, but like in technical terms, it's a lot more difficult because it involves like some automata.
So okay, then let's just skip it then.
Okay,
yeah,
I'll skip H. Yeah. Maybe Riley's want to talk about G, or I can talk about G if you want to. Let's make you try your microphone first.
Okay, I tried changing a setting. Is it better now?
Yes. Yeah.
It's a bit better, yeah.
Oh, it's actually better? Okay.
It's I would say a lot better. So
okay, I changed it must have been the Zoom setting for like removing background noise, but then you might hear people blasting music or something. I don't know. Okay, let me try to share screen then.
I don't know.
Okay, is it looking good?
The Tron, do you need to stop sharing or? I don't know. Yeah. Okay.
Okay, you can see my screen now?
Yeah.
Okay, so I
Let's
actually
skip F. Yeah, I
yeah,
think
F is pretty
yeah, it's too trivial. Yeah, let's skip.
okay. In that case, I can talk about E, K, and G.
Mhm.
Okay, so problem E is a bit intimidating because like statement's kind of long and there's lots of strings, but it's actually somewhat straightforward. So what it says is that we have a bunch of recipes like, huh? Oh, you don't see my screen?
Yeah. Oh, I can see your screen.
Okay, you can see. Okay.
Looks like trans computer is really slow.
Okay, so for example, a recipe would be like you can make a pizza tomato by taking a pizza base, adding the ingredient tomato to it, and by doing so, it costs 1, and it has you get two more prestige points. So it's kind of silly, but basically it's like we have a bunch of like food items we can make, and so for example, like one of them might be pizza tomato, one of them might be pizza base, and then we have recipes like you can make one into another by adding some ingredient. The name of the ingredient is not used for anything at all. That's just like filler string. And so then there's like a cost and a prestige to do this. It says if a if a menu item, if a food item does not have a recipe to make it, then it's an elementary dish. So that means like you can make it by default for 0 cost and 0 prestige. But then like everything else like is like this graph of recipes that it gives you. So it also guarantees some things like there's no cycle, so you can't make a dish from itself. What else does it say? It also says if there's multiple ways to make a food item, then you're only allowed to make the cheapest. You're only allowed to make it the cheapest way, and if there are multiple ways to make it the cheapest way, then you do the most prestigious, cheapest way. And then the final question is, you have a certain budget. What's the maximum amount of prestige you can do for like some set of menu items? So there's like 2 stages to this problem. The first stage is you want to calculate for each dish what is the what is the only allowed way that I can make it. So the answer would be like what's the minimum cost to make it, and given that if there's like ties, then you break it with prestige. So because it's an acyclic graph, you can do that with like dp. So like to compute, maybe I should say the arrows are the other way around, I'm not sure. But basically to compute this dp state, the dp state for this one, we need to know what's the cost to make all of its predecessors. So like we do that recursively, and then once we know all of those, then we have enough information to like to make this state. So we say like dp of I is like we have 2 things we compute, the cost and prestige. So then the question is, we have a certain budget and we want to maximize prestige for a set of menu items where we do not exceed the budget and costs. And then for that, you can just use like a knapsack DP. So one tricky thing I believe is how you do it will depend on whether you're allowed to make the same dish like multiple times. I forget which
This
one
one
it was.
doesn't. I think.
It
You
doesn't
can-
affect it too much. It's basically a knapsack
Yeah.
DP problem where the complexity would be like the budget times like the number of items. So is this good?
Yeah. So yeah, we did the we did Dijkstra for the first part, which it's I guess it's not needed because it's a DAG, but that
Yeah,
also
so
works. Yeah.
in a DAG, you can always do shortest, longest paths in linear time. Okay, I think I'll move on to K. So in problem K, we have a bunch of candles at various points on a birthday cake. And then someone will blow wind in a certain direction. And the question is like we're interested in like what's the strip, like what's the width of the strip that's needed to get all the candles, like if we blow in this direction. So like this width is what we care about. So we're not given the direction that is blown in. What we care about, like we only have the set of points, and the question is like what's the minimum possible width. Okay. So what I noticed is if we choose a certain direction, then the extreme points that it touches in either direction will lie on the convex hull of the set of points. So like we can compute the convex hull, and then like we need to find like ways to make two lines that like border the hull. So suppose we have like two vertical lines like this. We can always make the width, like we can rotate the points so one of the lines is actually one of the edges. Whoops. So we can always rotate it so one of them is one of the edges, and it won't like increase the width. So what I do is I iterate for each edge. What's the farthest point in this direction, like perpendicular to this edge? And the number of points is kind of large, so we can't afford to do that quadratic time. But what we can do is like a 2-pointers thing where we say like we fix this as index I, and then we like advance this second pointer J like counterclockwise as long as it gets further from this edge. So then when we advance to like the next edge, my mouse is being weird. So when we advance to the next edge, J will it will only go more counterclockwise. So it's like 2 pointers, and the complexity will be there's n log n for hull, for convex hull, and then the rest of it is linear time.
Cool.
Let's see, then the other problem is G, which I submitted but it got time limit, even though it's like this is the intended complexity. So maybe I'm bitter about that. So the problem is we have a restaurant, and there's a bunch of bottles at various points in the plane that need to be delivered to the restaurant. And there's a bunch of people also at different points, which we can hire to deliver the bottles to the restaurant. So the constraints are that, what was the word they used for this? Anyway, the people we can hire, they can only carry one bottle at a time. So if, for example, this person can't pick up bottle 1, then bottle 2, then drop it off at the restaurant. So they would have to like drop it off at the restaurant before they can go and pick up another one. Also, the distance is moving like Manhattan distance. So like you can only move like 1 grid unit at a time. And the cost is the total distance traveled by all the workers. So the problem asks, what's the minimum cost to hire some number of workers? You don't have to hire all of them. to deliver all of the bottles to the restaurant. And the constraints are like there's 1,000 of each. So what I realized, the first thing I realized is that when we like every time someone grabs a bottle, they always should take the shortest path directly to the restaurant, because they can't really do anything else. They can't pick up another bottle or something. So if we have, if we have the restaurant and we have every single bottle, like we always need to have these paths. Like that comes by default in our cost. So now I will think about how do we minimize all of the other costs, ignoring those. So in other words, we need to have some C's like matching up to the first bottle they pick. And we also might need to have like workers who leave from the restaurant after they drop off a bottle. So we would need to add edges like this maybe. So basically possible edges are like at most one coming out of a worker, or at most n-1 from the restaurant. So the reason for this is if all of the if all the workers came from the restaurant, then that means we're not actually hiring any worker to pick up a bottle. And if we have at least one worker, then they can satisfy everything coming out of the restaurant. So it's enough to just say like at most n-1. So you can use the restaurant at most n-1 times, and you can use each worker at most once, like for the first bottle they pick up. So this actually looks a lot like a assignment problem. So basically we think of the restaurant as itself like a worker that can be hired n-1 times. So like we have restaurant several times, then we have all of the workers C1, C2, etc. And then we have the bottles B1, B2, Bn. And then for each pair of these, like we connect it, we have a cost of the Manhattan distance between those 2 points. And that's the cost to like get a worker from this point to pick up this bottle. And again, the dropping off the bottle cost, that was already like pre-computed, and we don't have to care about minimizing that anymore. So we just have to solve like the assignment problem on this structure. There's 2 ways to do it really. So one way is like a min cost max flow, where we have like a source and a sink. So like each edge here has, or all of the edges have capacity 1, and then these edges have like a cost of the Manhattan distance. And then another way is the Hungarian algorithm, which solves it in a different way, but I think it's pretty similar. But yeah, it essentially reduces to like a somewhat standard problem, and I think they set the constraints and time limit like way too tight, so I got time limit exceeded.
So let's see what's wrong with a greedy approach. So if I get all the distance between all person and the bottles, and then I take the smallest one, and that one I have to use, and then that one basically get to the restaurant, and then I add the distance between the restaurant and each of the bottles. Then I just take the next smallest one.
So you're saying for greedy, are you saying that each bottle should be picked up by the closest worker?
No. I just the first one. So the first one is among all the pair of distance among the distance between all pairs of bottle and the person. I pick the smallest one. So then
Yeah.
then that person will pick that bottle and then go to the restaurant, and then that person's distance is all removed.
It might be like this distance is 1,
Mhm.
but then this distance is say like 2. This
So-
distance is 2, but then like this distance is like 100.
So
like, if you
which
did-
point are what? Yeah. Where's the restaurant here?
Well, let's say this is one
okay.
worker and then this is
Okay,
a
okay.
restaurant, and let's say these are like 2 bottles. Okay, so I guess maybe this doesn't work because of triangle inequality.
Mhm. Yeah, but that, yeah, just.
but in principle, something like this could exist, or a more complicated thing. But
Okay.
if you did greedy, then you would say 1 is the cheapest, and then of the remaining ones, 100 is the cheapest. But really, the best way is 2 and 2.
I see.
So something like I
I
thought.
see.
I thought of a few different greedies. Like
I see.
if you choose the closest worker, then what happens is you might choose the same worker twice, which isn't right. Or if you-
Right, yeah, but yeah, okay, so it could be
Or-
better to. Okay. Okay. Mhm.
So I think
So are we
that's,
done? Or?
I guess we didn't talk about I, but
Yeah, we don't
I
have to
didn't
talk about
try to-
everyone. Yeah, I think that's okay. Good. Okay. Thank you. Thank you, guys.
Thank you.
Goodbye.
All right.